Fred, answer the questions now as quickly as you can. Who, what, why, where? Go.
SPARK Microsystems, wireless connectivity company. Why? Low power connectivity, low latency connectivity. Where? In all your wireless constrained applications.
Hello, IPXers. We are at the world famous, maybe not so world famous. Is it world famous? I don't know. I always say it's world famous, so it must be. Fred from SPARK Microsystems. We're going to find all about what Fred does at SPARK Microsystems. So, Fred, tell us about SPARK Microsystems.
Sure. SPARK Microsystems is a company based in Montreal. We are a company making wireless chips in order to solve a lot of problems, and I'm sure we'll be talking about that.
I hope so. So tell us about your wireless chips. Tell us what happens if SPARK Microsystems didn't exist. What would be a design engineer doing if for some reason they were having an off-planet moment and didn't realize that SPARK Microsystems exists? What would be their legacy design solutions today?
Sure. Well, a wireless designer is going to have a lot of connectivity problems. Number one, they're going to want to connect maybe a mouse to a dongle. They're going to want to connect a headset to a computer, sensor to some gateway, et cetera, et cetera. And typically, you want to get that data through as fast as you can and with the lowest energy cost. And the issue here is, as ironic as it sounds, most often than not, the wire, right, is going to be where you're going to go, simply because it kind of solves all that, right? It's point A to point B, connected. It's a 100-year-old technology, right? We all know the wire very well. So that's one thing, right, with regards to wireless. And that comes with a lot of limits. And I think they come into 4 flavors. So the first one is communication delay. Right. So wireless technology inherently has communication delay between point A and point B. And frankly, you can actually perceive it. And I think we've done a demo with you guys to show that. And you really see, or I should say hear in that case, because it's an audio demo.
So we're going to look at 3 examples. First of all, with wired, second with BLE, and then with your solution. Because what we're trying to explore is the differences in latency in those 3 different approaches.
Exactly.
Fred, over to you.
Yeah, so essentially we have 3 paths here. We're sending 96 kilosamples per second, 24-bit audio. That's uncompressed. That's an important point with our technology. Of course, the wire, we said it a few times already, can do it. All right. And then Bluetooth can't do the uncompressed, so we had to use a compressed audio stream, but we'll be able to show the difference. So right now we have a wire that is connected through a electronic drum set through the speaker. And surprise, surprise, when my assistant Radley here hits the drum, you can see that there's no latency.
I think the human ear tells us 0 latency.
We're fine. So now what we're going to do is we're going to add Spark to that. So now we got 2 EVKs, and now the audios are combined.
Yep.
So it's hard to perceive the latency.
It's there, but
you got to really kind of focus.
Yep.
And now if we go and add Bluetooth to that, so now we got 3 streams.
Yep.
So the first talk you hear is the wire and Spark, and the second one is Bluetooth.
Yeah.
So now you can perceive the latency, and remember that's Bluetooth using compressed audio, right? Whereas we're doing it with uncompressed audio.
That's as good as you're going to get for Bluetooth.
Exactly.
You hear the latency and you're like, okay, that's not a wire, okay, and that's of course Bluetooth. So that's what the designer has to live with, and that will transpose itself into issues, because if you're controlling a robot or you're using this in some interface system, you just can't afford the delay. And again, you jump onto a wire, right? Because the wire speed of light, it's all solved. Then you've got the bandwidth, the throughput, right? You want rich experiences. You want a mouse that has haptics, vibration. You want a system with video. You don't want to have this highly compressed audio stream. You want this rich experience. But again, if you want that, and you'll say, well, Wi-Fi is great. I can get gigabits per second of data throughput with Wi-Fi. But unfortunately, the battery requirements for Wi-Fi are just not compatible with most devices that have to be mobile, right, or portable. So then you go to Bluetooth, and then you're stuck with 100 kilobit per second, maybe 200 kilobit per second, and then you have this really, constrained pipe to get your data across. So then your experience can't really be, I would say, as rich as it can. You can't do head tracking on your headset. You can't do uncompressed audio. You can't have a brain-computer interface because there's just too much data to chug through wirelessly. So again, you go, and I'm sounding maybe like, again, a broken record here, but you're going to go to a wire again, right?
No, well, no. I asked a question about legacy, so this is a very good background. This is the things that we need to understand, which is why we're going to lead to Spark Microsystems as to why you are going to be the solution. So I don't
Sure.
think you do sound like a broken record. I just think we're going through. I think we're just going through quite nicely, going through what would be the scenario if you didn't exist. That was the question I asked, and now you're going through those scenarios.
Indeed.
So absolutely. So I don't
So-
think you are sounding like a broken record at all.
Yeah, exactly. And then if we go to number 3, then the power consumption, and I kind of hinted at that earlier, right? Most people want wireless in a device that's mobile, right? It's not a device plugged into the wall for obvious reason. Otherwise, well, might as well again use a wire, right? It's already plugged into the wall. Why am I going to have wireless with it? So, but that means you need a battery, and if you need a battery, you can't burn a lot of power for your wireless function. You already probably have tons of things this thing is doing on top of communication. So power consumption will also limit you. And again, you'll have Wi-Fi, great, but then, well, I can't get good battery life. So nobody wants a half an hour mouse battery life, or a brain computer interface where I have to implant a battery into the brain. Not a good idea, right? So power consumption is a big thing. And finally, and this I feel power consumption people relate to. Everybody gets the whole battery thing, but the interference thing, and people also get that. You're at the airport, you're using Wi-Fi. Everybody knows it's not going to be a great experience. You're going to get dropouts. You're going to get disconnects. Sometimes even you can't even get the Wi-Fi to connect. And interference is the issue because you want this experience to be rich. As I said, you don't want this delay, all that, but you want it to work. Right? You want to get all those bits through, and you don't want to lose any data, because if you lose data, well, your audio will break down, or worse, some mission critical piece of information will be lost. So that's, I would say, the fourth leg here is the robustness to interference. And yet again, right? What do you do to fix that when you're at the dead end is a wire, right? Because a wire can be shielded. And obviously that means all the interference is shielded from the signal that you're looking to transport. And again, that's where wireless is not necessarily as good at. And that's where wireless is getting even worse at it, because as more people use wireless devices, you're getting saturated. I mean, just Wi-Fi, for example. Everybody also sees that if you live in a condominium or some apartment building or downtown, I mean, it's even a challenge for just that. So imagine if you're going to start having billions of devices that are from your fridge to your mouse to your, exactly.
Or maybe having two teenage sons doing live gaming while you're trying to
yes,
do something as simple as your email, and they suggest for 1 minute that their gaming is more important than your business email. That might be an experience that somebody on this particular podcast has had regarding Wi-Fi, and the many debates that you have. That's what goes on in my very small, tiny little life. But
now,
yes, that you're just describing exactly the same complications, but I'm just bringing it back to me. That's how complicated Wi-Fi can be.
It's funny. I would have thought the communication would have been the other way, where those teenagers would come to you complaining that you're hogging the system. But
yeah, how dare I do my business email during the working day and get in the way of their gaming? Yes, I know. Of course, I'm wrong. Silly me. Yeah. Okay. So. Moving on. So we're talking point-to-point communication, and you've just explained very nicely how that at each point, literally from point to point, there is compromise if you're not going to use a wire, be that power, latency, availability of signal, all those kind of things. So that's what the design engineer faces today. So, and then SPARK Microsystems comes along and says, right, we recognize those 4 things, and we're going to give you a solution. So now now you do exist. Tell us how SPARK Microsystems goes about solving those problems for design engineers who are facing those problems today.
Yeah, so as I said earlier, we're a company that's now 9 years old. Our claim to fame, and our goal and our mission was we want to bring wireless to be as close to a wire as possible and fix all that we just been discussing together today, right? So we wanted the experience of devices using our chipset to be as close to what you could do with the simple wire. But the issue is, as simple as that mission is, we realized that it wasn't easy for a wireless radio to do this, and it took us about, I would say, several years of R&D and a lot of headaches and hair pulling, but we finally got it, and now we have this chip, and it's able to provide you with a lot of capabilities. And some examples include gaming mice, where the gamers want their mouse to be as fast, as responsive as possible. Gaming headsets, same thing. Audiophile systems, where you want that audio to come through perfect, but you just don't want to use that wire, right? Because first, they charge you a fortune for those audiophile wires, and B, it's not the most aesthetic and very expensive to install, and so forth. So that's the company's mission, right? Bring wireless to be as close to a wire as possible, with as little trade-offs as possible.
Right. And how do you measure that in terms of a design engineer? You spoke about those 4 things, which are all absolutely true, and we understand them. How are you able to say to a design engineer? Obviously, maybe we'll talk in a moment about development environments and how they can evaluate your technology.
Yeah.
But today, how are you able to compare your solution to a wired solution? Are you able to say, right, we are 99% there on that one, and we're 99.5% there on that one, and we're 87%? How do you go about verifying against those 4 things that you just described to show this is as good as it's going to get, other than with a wire?
Sure. Let me give you, I would say, examples that wireless engineers and companies would probably understand, just to give a relative comparison. So when you want to do wireless, you're usually going to go to Bluetooth low energy, right? That's kind of the de facto low energy wireless technology out there. So when it comes to communication delay, typically you're going to be stuck north of 50 milliseconds, and most of the time, due to all the trade-offs that I mentioned earlier, you'll be in the hundreds of milliseconds. And to the engineer, that probably speaks, but to the layman, that's still perceivable. You're going to still, again, if you listen to an audio stream with that kind of latency, you'll be able to tell. So you can imagine the havoc that will cause on your system. So SPARK Microsystems brings that latency down. Because our wireless radio has a latency profile that's in the microseconds range. So that means your application then can have much lower latency than what you do with Bluetooth, for example. We do single-digit millisecond audio transport, for example. So from hundreds of milliseconds to single-digit milliseconds. For example, we have a guitar amplifier demo for 3 millisecond latency. And it's a funny story, because we had, I would say, a renowned, guitar maker telling us, well, I play the guitar and I can tell between 10 milliseconds and probably 3 milliseconds. So we pushed us to get down to 3. And then I think at 3, I would say then it becomes like, can you really taste a $10,000 bottle of wine or not? I mean, at that point, you are looking and,
not that I've ever had a 10,000 bottle of wine, but I'm pretty sure the answer to that is no.
So anyway, so that was one. Then when we look at, so that's communication delay, where tangibly we can bring an edge. When it comes to the throughput.
So sorry, just to come back to that, come back to that, what actually counts there, because you're talking about consumer devices like gaming or an amplifier with somebody playing a guitar. What you're actually talking about is the perceptible human engagement with that you can tell the difference. I mean, you can measure it on a display and say it's X amount of milliseconds, and can we get that better or not? But the real difference is, can a human being perceptively tell the difference between whether it was wired or whether it wasn't? And you're saying you've absolutely got to the point where you can't tell the difference.
Exactly. And of course, I like to talk about human relatable examples, but of course, machines care about latency and delay as well. So for example, we've got companies that want to do head tracking. You move your head, it processes the motion, it then plays with the audio. They do all this on the headset, cost a fortune in hardware to do that. And they wish they could send the data to the computer and back to the headset, because much cheaper to process all this data on the computer to, do all the stuff when you move your head. But the delay of Bluetooth is just such that it's never going to work. You're going to have to go from your head all the way to computer, 100 milliseconds. Oh, okay, process on the computer. Then go back to the head, another 100 milliseconds. Forget it. By the time you move your head, you're
Yep.
going to probably be completely sick by the motion sickness this thing will bring because it's too delayed, right?
Yeah.
So that's another example
Absolutely.
of why delay may not be just always just human focused, but I like to bring the human example because I feel it's just easy to grasp.
Yeah. So there's a computing essence to that as well, which is
Yeah,
if a robot is reacting to something or there's some sort of computer vision or something,
correct.
you can't have it because it'll that latency will just accumulate up to be ridiculous after
Indeed.
even after just 5 seconds, you're just out. You just won't make any sense.
Yeah, absolutely. Robots, right? You don't want robots to
Yeah.
collide. But if it takes them too long to figure out they're going to collide, well, they're going to hit each other. So then, what do you do to
Yeah.
fix that? You can't have a wire. Obviously, you're not going to have wires stringed between all your robots. That'd be crazy. You just may have a safety zone or a safety bubble of X meters around them, and the more latency, the more safety bubble size you need. But then, obviously, you can't have as many robots, and they take more space, less effective, less efficient. So, or you have to move them much slower, right? Make them turtle
Yep.
pace so that by the time they get the signal, they were moving so slow that, okay, now I can stop. I'm about to collide, right? So this is where delay start to have these other more, I would say, subtle effects.
Yep. Yep. So should we go through those other two or three things that you mentioned, each one knocking them off and explaining how you solve that problem?
Yeah. So data throughput, as I mentioned, Bluetooth 100 kilobit per second, 200 kilobit per second. So people use audio compression, for example, and yeah, great, but not really the original qualities. By no means the headsets you have on your head right now are giving you CD quality audio. You may not be perceiving that, but they're not. Ironically, a $1 earbud you'll buy at Dollar General or some dollar store will give you better audio quality than those nice headsets you have, right? Because the wire, again, has the bandwidth. So Spark brings that bandwidth from a few hundred kilobit per second for Bluetooth to, in our case, we go up to a 20 megabit per second payload. And that gives you, okay, it's not quite Wi-Fi level, obviously, but Wi-Fi, as I mentioned, has its own issue, but it gives you, an order of magnitude, even actually 2 orders of magnitude more data to play with. And that's where you can start thinking about, hey, I want to do video transport now. Oh, I want to do uncompressed audio transport so I get my CD quality without having to compress. Or, oh, all of a sudden I can take this brain data that my brain computer interface needs and stream it across in real time, right? Without having to drill a wire through the head, right? So all these things, I think, make a big difference when it comes to the data throughput. So that's number two. When it comes to energy, right? I mentioned power consumption, very important piece. We have an order of magnitude better energy efficiency than Bluetooth when it comes to transmitting a bit from point A to point B. So what that means is, okay, you're using more data, as I just said, right? More data throughput, but the energy consumption still is very manageable and well aligned to mobile devices like headsets, mice, implants, all of the above, right? So that's the third piece. And finally, on interference, and I mentioned examples earlier, Bluetooth is not, I would say, very good at dealing with interference. And a good example is you're probably going to, once in a while, hear a click in the audio or a complete dropout. You kind of just shrug it off. And frankly, they use a lot of tricks to hide those blips because audio, well, luckily, I guess, you can do tricks to trick the brain to not really hear errors. But you can imagine in a lot of applications, you just can't do that, right? You just need the pristine data and you can't live with it. So we have a radio that, unlike Bluetooth, and Bluetooth is stuck at 2.4 gigahertz. And of course, Wi-Fi is there. Everybody but the kitchen sink is in that band. So interference is a big issue. In our case, we have an agile radio that operates from 6 to 9.2 gigahertz. And it has basically 3 gigahertz of bandwidth to be agile. So it's able to, I would say, wiggle its way through, for lack of a more, I would say, scientific term, and get the data across no matter what, even if you have a significant amount of interference. It's easy to jam 2.4 gigahertz. You can get open source hardware to jam 2.4 gigahertz, and that will kill your Wi-Fi, your Bluetooth, but it's very hard to jam 3 gigahertz of bandwidth. And that, I think, is the beauty of our technology, is we are agile, we're able to get through the data no matter what.
two last questions to understand for a design engineer, because this is all about professional design engineers trying to find solutions to their problems. You are very eloquently and you described those 4 areas where you could have Bluetooth, you could have a wire, or you could have Wi-Fi. So obviously you're working, what you've described is you've just more or less got to the absolute point where you're just as close to a wire as any technology could be. But that's quite a premium technology. So at what point is there a point at which this a price point? So are we only looking at premium products in like industrial robots or consumer devices or gaming, or is there more typical Wi-Fi, Bluetooth type examples where this technology can be applied? Just help the community understand, because if you're in the business of it doesn't really matter, and I'm going to be making 1 billion of these things and it doesn't really make any difference, then obviously you might say, well, hang on a minute, we might not be the right solution here. So just help the community just understand the point at which this very clever technology, which gets you as close to wired as you could be, but of course there's a premium to that. So just help them understand that.
Yeah. So when we started the company at the time, we really had a vision that it had to be relatively low cost technology. Okay, I say relatively low cost because the bottom's the limit. We all get that. So the technology, for many reasons, has been built to require low cost bill of materials. We don't need fancy crystals. Like, frankly, I think our bill of materials may be lower cost than most Bluetooth chips, ironically enough.
Oh, okay, that's interesting.
So our chipset, I would say, is very reasonably priced. You can go check on DigiKey and other places. And in volume, I think we can definitely be compatible with consumer electronic products, which are, I would say, the ones that have the most price pressure. That's not by luck or by choice, it's by design. It took a lot of work there. We don't necessarily market that feature, right? We've been talking about 4 things, but I love the fact you're bringing cost to issues, because it's great to have these 4 things, but if it's a $20 chip or even a $10 chip, you're not going to get there in most of those applications. No. So the technology, I would say, is very friendly on the cost side. We provide a lot of the support when it comes to the antenna integration, of course, the software integration, and I'll talk about that when I give you a bit more about what we can give designers in a second. I guess that might be your second question. So,
yes, that is my next question. Next question. Am I that one-dimensional? Clearly, I am. So let's talk about that now. Let's talk about I've understood where you go. I've understood that actually there's some price points that I may not have to worry about because of clever integration and bill of material issues that you've dealt with. So now I'm at the point of, right, I want to try and find out whether this is right for my application. What's the environment that I get? Is there an evaluation board? Is there software? What is it that I go and get so I can work out whether this is me and whether this is going to help my nearly wide application?
Indeed. So we have we're a chip company. So obviously the key product here is the chips that you buy. But we have an evaluation kit, which is a board. You get a pair of those boards. You can then use a very nice GUI to configure the link to whatever your application would require. And then you're able to essentially check the robustness, check how good the link is. Can you put the antenna in a particular position for your application? Will it still work? So you're able to preview that. Then on those same boards, we have a software development kit you can run to develop your applications. Well documented. Documentation's on our website. It's really accessible. And we bring you several examples, right? Audio and so forth examples. We also have reference designs. Now, when I say reference design, what do I mean? I mean hardware layouts, source code for the application, obviously documentation. Even we'll provide customers with test data of what that device can do with our chip. We've done that for mice. We've done that for headsets. We've done that for even IoT tags that use our technology. So there's a lot of reference designs as well that I would say augment the offering beyond just a software development kit or basic examples. So that's kind of the whole story. And I think importantly in the wireless space, the antennas. We have an antenna team embedded in our company, and that allows us to support and provide freely antenna designs. And I've seen a lot of publicity on ultra-wideband antennas, and it's great to see that. But I would say you're getting the probably some of the best ultra-wideband antennas in the world from SPARK Microsystems freely, let's be honest. And all you have to do is use our chips, and that's a big part of the complexity of using our technology is the antenna. I mean, RF is hard. Antennas are a dark art, as you may have.
They do. We have videos on that, and we even call them a dark art. We've decided that they're a dark art. So it's not that you're describing something we haven't already described. In fact, I think we did actually have a thumbnail that says the dark arts of antennas.
Indeed.
No one seems to understand, apart from the antenna people who do understand it, fortunately.
Indeed.
Good.
We think that's a great asset that we bring to the table on top of everything else. Yeah.
Excellent. Fred, thank you very much for joining us on IPXchange. Thank you for explaining what SPARK Microsystems do, how you bring the world of nearly wired, but just as good, quite frankly, if you weren't wired, and you've pointed out the 4 things, well, I put up 5 fingers. That's a bit strange, isn't it? Four things, 1 thumb gone. 4 things that you should be looking at how you can bring nearly wired communications to your systems, and then how you can evaluate it. And you get the dark art of antenna, not for free, I'm sure, but embedded in with the system, which makes your life a lot less complicated. Thank you very much, Fred. Very nice to meet you.
Appreciate the time.
Enjoy the rest of your day.
Yep. Cheers.